Sustainability of Palm Kernel Shell Ash, Pksa, as SCM in Self-Consolidating Concrete, SCC, Design. Abstract. This research work investigates the rheological, fresh, and hardened properties of self-consolidating concrete, SSC, with palm kernel shell ash, Pksa, as supplementary cementitious material, SCM. The experimental tests adopted for fresh properties of SCC in this research work was mainly the Slump Flow test, Lbox Test, V-funnel test, and T50cm as per 1 standards. The mix design was iterative mix design method of 5 different proportioned mixes of 0%, 5%, 7.5%, 10%, and 12.5% replacement of cement with Pksa as SCM. The mixes were prepared in conformity with 1 specifications. A total of 45 cube samples, 150 mm x 150 mm, and 15 cylindrical samples, 150 mm x 300 mm, were used to examine the hardened properties of SCC experimentally. The cube samples were tested for compressive strength at curing ages of 7, 28, and 56 days, while the splitting tensile strength test was performed on the cylinder samples after a curing age of 28 days. The results of investigation revealed that all the fresh properties of Pksa blended SCC were within the obtainable standard in 1, and the compressive test results showed that 0% 0F Pksa produced 41.33 N/mm2 at 56 days, 5% produced 38.40 N/mm2, 7.5% produced 36.71 N/mm2, 10% produced 33.78 N/mm2, and 12.5% replacement of cement with Pksa produced 29.50 N/mm2 at 56 days. The splitting tensile strength test gave strengths of 3.36, 3.18, 3.16, 3.01, and 2.68 N/mm2 for 0%, 5%, 7.5%, 10%, and the 12.5% levels of replacement of cement with Pksa respectively at 28 days. From the results, it could be that SCC can be produced by substituting cement with Pksa up to 12.5% without compromising the workability and the strength of the SSC produced. Keywords: SCC, Pksa, pozzolana, additives, strengths. Introduction. Material usage in concrete production would indeed be an interesting area to be studied and investigated. The readily available natural materials can be applied in concrete production as alternative for aggregates, cement, binders, or filler to ensure industrial and ecological balance as defined by 2. Industrial ecology is a practice which tends to substitute the naturally occurring materials with waste, byproducts, of an industry. Palm kernel shell ash, Pksa, a pozzolanic material gotten from the calcination of palm kernel shell readily available as a waste product from the oil mill industry, can be used as partial substitute for cement in self-consolidating concrete. It's applicable in a number of ways, among which are buildings, roads, bridges, dams, retaining structures, stadiums, airports, etc. And due to this wide range of its application, the natural law of demand sets in, and this lead to an increase in its price. According to 3, its usage is around 10 billion tons per year, which is tantamount to 1 ton per man. With the world population increasing at a geometric rate, the need for shelter, infrastructure, and workplaces also increases, as these are the essential needs of man. Self-compacting concrete, SCC, a new kind of high-performance concrete, HPC, with excellent deformability and segregation resistance, was first developed in Japan in 1986. It is a special kind concrete that can flow through and fill the gaps of reinforcement and corner of molds without any need for vibration and compacting during the placing process. Additives or admixtures are used to alter and improve hardened properties of concrete. They may enhance the durability, workability, or strength characteristics of a given concrete mixture. A lot researches had been done on the use of mineral additives other than Pksa, such as high-volume natural pozzolana and limestone 4, coconut shell aggregate 5, palm oil fuel ash 3 rice husk ash, sawdust, and palm kernel shell 6, ground nut shell ash, GSA, 7 and periwinkle shell ash, PSA, 8. Mate trials and method. Materials used. Materials used for this study were, cement, palm kernel shell ash, Pksa, fine aggregate, Fa, coarse aggregate, Ca, water, superplasticizer, Complast SP430. The cement utilized in this study was grade 32.5 cement which satisfies 9. The shells were collected from a local oil mill located at Ikoyi in Ikoyi, Asun State. Thereafter, they were washed, filtered thoroughly to remove sand and other particles and sun-dried. The shells were weighed and burnt into ashes at the Foundry Laboratory, University of Ibadan in the furnace at a temperature of 800-10,000 C as obtained from the Chappelle's test conducted on the ash. The chemical and physical analysis of the Pksa and aggregates used are presented in Table 1 Table 3 below. The aggregates complied with the requirement of 10. Superplasticizer, SP430, conforming to 11 was also used to improve the rheological properties of the concrete. Experimental work. Chappelle test, one of the tests used in determining the reactivity of pozzolanic materials as well as their optimum calcine temperature. The test followed 12 as stated by 13. Based on the result obtained from the test, the Pksa used for the study was obtained from palm kernel shell calcined at a temperature of 8500 C. Sieve analysis of fine aggregates was carried out as specified in 14 using sieve size of 6.3 mm 4.75 mm 2.36 mm 1.18 mm, 600 300 150 and 75 as shown in the Table 2 and Figure 1 below, and the coefficient of uniformity, Cu, and coefficient of curvature, Cc, being 1.45 and 0.96 respectively, with the percentage passing the 600 sieve being 47%, which is less than 51% as stated by 12 in his book, Self-Consolidating Concrete. Applying what we know that sand to be used for SCC production, the percentage passing the 600 sieve shouldn't be 51%. Proportion of samples. After series of trial mixes all aiming at designing a mix that will conform to the one specification, and based on the specification, a mix design was adopted and the mix design combination is shown in Table 4 below. 3 results and discussion. The tests to be carried on self-compacting concrete are in the dimensions which includes the fresh state property tests and the hardened state property tests. The fresh state property tests. For a self-compacting concrete mix to be workable, the mix must be subjected to the 3 important tests: filling ability, passing ability, and segregation resistance test, to be carried out on the mix in its fresh state. In this research, the slump flow by Abram Cohn and the V-funnel was adopted for filling ability test, the V-funnel at T5 minutes for the segregation resistance, and the Lbox test for passing ability as shown in Table 4 and Figures 3 to 7. The tests were carried in order to ensure that the SCC produced passes the required tests as specified in 13 guidelines for SCC production. The apparatus for the tests is shown in Figure 2 below. For the hardened state property test, compressive strength test was carried out on the cubes at all levels of replacement, including the control at curing ages 7, 28, and 56 days. Also, splitting tensile strength was as well carried out on the cylinders at all levels of replacement, with the control inclusive at a curing age of 28 days. Slump flow test method. The slump flow is the test used in the assessment of the filling ability of self-consolidating concrete, SCC, i.e. its ability to flow under its own weight in the without blockage. The test was carried on the fresh concrete mix by the filling the freshly prepared SCC into the cone without vibration, compaction, or any form of consolidation. The cone is lifted and the SCC is allowed to flow. The suggest 3 classes for the slump flow according to the final spread, which are SF1, SF2, and SF3, with flow diameters 550 to 650, 660 to 750, and 760 to 850 respectively. Lbox Test Method. The Lbox test is a test used to access the ability of the SCC flow through when obstructed by reinforcements. For a good SCC mix design, the blocking ratio, H2/H1, must fall within the range 0.8 to 1.015. It is an indication to the slope of the concrete when at rest, i.e. an indication of passing ability, or a reveal of the degree to which the passage of concrete through the bars is restricted. The 15 suggests two classes according to H2/H1 ratio, PA1 and PA2 with passing ability equals 0.80 with 2 bars and equals 0.80 with 3 bars. V-funnel test. The V-funnel test was conducted according to 15 guidelines to evaluate the filling ability and the V-funnel at T5 minutes for the segregation test of SCC by measuring the time the concrete needs to flow through the V-funnel under its own weight. The 15 guidelines suggest two classes according to the V-funnel time, VS1/VF1 with T50 spread time equals 2 and V-funnel time equals 8, VS2/VF2 with T50 spread time 2 and V-funnel time 9-25 seconds. Hardened Properties of Scc. The hardened state property tests are the tests which include the compressive test and the splitting tensile strength test were conducted on the Scc in its hardened state. Compressive strength test of Scc. The cubes were tested after curing age of 7, 28, and 56 days at all levels of replacement including the control mix. The compressive strength was computed by dividing the ultimate load by the cross-sectional area of the cube. 3 specimens were tested for each of the curing days and the average of 3 values is then taken to determine the compressive strength of concrete. The test was carried out as described in 14. As presented in Table 5 and Figure 8, the compressive strength of Scc ranged from 12.36-18.67 N/mm to 27.47, 32.66 N/mm to and 29.56, 41.33 N/mm to at 7, 81, and 56 days respectively. Generally, the strength increases with the curing age for all the prepared mixes. The compressive strength of Scc at 7 days, 21 days, and 28 days were 18.67 N/mm to, 32.66 N/mm to, and 41.33 N/mm to for 0% Pksa, 16.44 N/mm to, 30.44 N/mm to and 38.40 N/mm to for 5% Pksa, 15.78 N/mm to, 29.99 N/mm to and 36.71 N/mm to for 7.5% Pksa, 14.22 N/mm to, 28.36 N/mm to and 33.78 N/mm to for 10% Pksa and 12.36 N/mm to, 27.47 N/mm to and 29.56 N/mm to for 12.5% Pksa, respectively. The percentage variation in compressive strength of Scc dosed with 5%, 7.5%, 10%, and 12.5% Pksa as expressed in terms of their control sample, 0% Pksa, were -11.9%, -15.5%, -23.8%, and -33.8% respectively at 7 days, -6.8%, -8.3%, -13.2%, and -15.9% 28 days, -7.1%, -11.2%, -18.3%, and -28.5% at 56 days respectively. From the results obtained as shown in the charts and tables, it could be observed that the compressive strength of all the samples under study regardless of their levels of replacements, 0, 5, 7.5, 10, and 12.5% Pksa, increased with time but though lower than that of the mix without Pksa irrespective of curing age. This work contravenes the works of some researchers 17, 18, with the research findings of 17, it could be observed that, in all sample mixes of the self-consolidating concrete incorporated with Pksa under study, there was reduction in their strength when compared with the mix without Pksa, as the strength decreases with increasing percentage of Pksa content, and this agrees with conclusions drawn from the research and findings of 18. However, the obtained results in this research is in line with the findings of 16, as the same trend was followed when he replaced cement with Pksa in terms of compressive strength properties. Splitting tensile strength test. In an attempt to determine of the split tensile strength of self-compacting concrete samples, 3 cylindrical shaped specimens of diameter 150 mm and height 300 mm cast earlier at all levels of replacement including the control were crushed with the cylinders lying on their sides. The tests were conducted on cylinders at a curing age 28 days. The results obtained from the tests are tabulated below. The results of split tensile test obtained at 28 days are displayed in Table 6, while the graphical illustrations of result are presented in Figure 9. The split tensile strength dosed with 0% Pksa, 5% Pksa, 7.5% Pksa, 10% Pksa and 12.5% Pksa were 3.36 N/mm2, 3.18 N/mm2, 3.16 N/mm2, 3.01 N/mm2 and 2.68 N/mm2 at 28 days respectively. From the results, it can be deduced that the splitting tensile strength of the samples decreased as the Pksa dosage is increased, as they were less than the control at all levels of replacement. From these results, the reduction in strength of SCC incorporating 5% Pksa was -5.4, 7.5% Pksa, -6.0%, 10% Pksa, -10.4% and 12.5% Pksa, -20.2%. However, the split tensile result of SCC obtained from this present study corroborates with the deduction made by 19, as the same trend was followed in their research. For conclusion, the rheological properties of self-compacting concrete for 5 mixes of SCC with being substituted with Pksa at various levels, 0%, 5%, 7.5%, 10%, and 12.5%, with the 0% acting as control were determined. The hardened state property tests carried out on the SCC with the same levels of substitution of cement with palm kernel shell ash were the compressive and the splitting tensile strength tests. This chapter presents the conclusion and recommendations drawn based on the research work conducted in this study. From the results obtained from the tests carried on a mix of SCC with 0, 5, 7.5, 10, and 12.5% levels of replacement of cement with Pksa, the following conclusion and recommendations were made. Palm kernel shell ash, Pksa, was found to contain virtually all the main chemical elements of cement, though in varying proportions compared to that of cement, which means it can replace cement in a quantity. The results obtained from the study encourage the use of Pksa as a pozzolanic material for partial cement replacement in production of SCC, and this will to a great extent reduce the cost of production, ecological problems, and the landfill area required for the discarding of palm kernel shell. The workability of the mixes of SCC incorporated with Pksa as partial substitute for cement at 0, 5, 7.5, 10 and 12.5%, conforms to the 13 specifications for self-consolidating concrete, as the results obtained were within the upper and lower limits. From the results obtained as shown in the charts and table, it was observed that all the sample mixes under study, 0, 5, 7.5, 10, and 12.5% Pksa, all recorded a reduced compressive strength values as the percentage of the Pksa content increases regardless of the curing age. The use of feasible superplasticizer agents in self-consolidating concrete production is a key to achieving a mix with satisfactory properties. V. Acknowledgement. We acknowledge the contribution of Department of Civil Engineering of the University of Ibadan, Nigeria towards the conduct of this research. We also acknowledge the guidance and support of Ngwola Labaran, Ph.D., for granting the access to his laboratory for research practical work.